Hello, everyone, and welcome to FusionEPtalks, a student-led webinar platform for sharing knowledge about nuclear fusion, science, and engineering. I am Jose Trueba, and I would like to introduce our speaker today, Aneeqa Khan. She's going to talk us about phasing materials for plasma phasing materials for the tokamaks and fusion devices. And she's already have working in a kind of a new material for this. She's going to talk us about the tungsten-diamond composites for fusion applications. So the talk is going to be about the developing of this material for fusion. Without further delay, I give the floor to Aneeqa.
Thank you, Jose, and thank you for inviting me here. It's really my pleasure to be here and to give this talk. Today, I'm going to be talking about developing tungsten diamond composites for fusion applications. And I'd like to thank my colleague, Dr. Stephen Lisko, who's, I hope, here today as well for his enormous contributions to the talk. So to start off with, I'm going to set a bit of context just in terms of the materials challenges that we face in the fusion community. So this map always really impresses me of the tokamaks that are all around the world, just reiterating what a global challenge fusion research is and materials research in fusion as well. Across the globe, we've got, these are just tokamaks, not to mention all the other type of fusion devices. So it's a really massive challenge and one that we all need to be working together on in terms of solving it. This also sits within our roadmap towards fusion energy. So here is the kind of in the middle, the typical European fusion roadmap, where we've gone from JET, we're building ITER, and the plan is to build a demonstration fusion plant feeding into commercially viable power plants in the future. In parallel, we also have the UK program, which is running at the moment, so the STEP program, which stands for Spherical Tokamak for Energy Production. They aim to build a prototype reactor by 2040, again feeding into this roadmap going forward. And also in parallel, there's a huge number of public-private partnerships and just private companies at the moment who are trying to develop things even faster. So it's a very ever-changing kind of landscape that's going on at the moment. And that means a lot of people who have maybe the faster kind of timelines are using existing materials in like the first generation of plants that they aim to build. But this means our materials program needs to also be looking further in the future, and we need to be looking at real other alternatives and better materials now as well, before it's too late. So this is also something to keep in mind. Here is just a reminder. I'm sure everyone who is watching here today is aware of this reaction on the screen. This is our candidate reaction for fusion reactors going forward. So it's between deuterium and tritium, producing 14 MeV neutrons and helium. I'm showing this because this heavily influences what materials we use and what are the challenges that we face in a fusion reactor. So as I mentioned, we produce 14 MeV neutrons. These interact with our materials. They can produce various damages, cascades, transmutation, etc. Within our materials, and they're real pain. There's so much more higher energy than fission reactors, and it's something we really have to take into account when designing materials. The other one is the heat loads that we're going to experience in a fusion reactor. So in ITER, during steady state operations in the divertor region, we're expecting around 10 megawatts per meter squared, which is a phenomenal amount of heat loads. And during transient events, that can go up to 20 megawatts per meter squared. So very, very high heat loads. The next thing, as a fusion community, we've decided that we want to have reduced activation materials. Whether this is really possible or not with the timescales that we were mentioning in the previous slides is another question, but it is kind of a boundary condition that people have set, that we want to reduce the amount of waste we produce. So we do have to take this into account, especially when we have so many 14 MeV neutrons kicking about. The other one is the helium, which I mentioned is produced from the DT reaction. But this also can be produced during transmutation from the neutrons as well in the materials in the wall itself. And this can interact with material, producing bubbles, blisters, and in tungsten we see things like tungsten fuzz as well. Then we have the more general, just plasma material interactions, which are always a challenge, and again cause kind of modifications to our materials, can lead to erosion, which is both bad for the material and also bad for the plasma, depending on what the material is made of. Then, if we're talking specifically about magnetically confined fusion, the magnetic fields we produce are massive. In ITER, we're expecting around 13 Tesla as the maximum magnetic field. And to put that in perspective, if you think about a PET scan in a hospital, that's only 1.5 Tesla, and that's already very, very high. So the magnetic fields can influence our material performance, especially if we're talking about things like liquid metals. And as well as the impact of the magnetic fields on the materials, we also have the materials needed to produce the magnetic fields themselves, which is another huge challenge. Then we also have tritium being produced from this. Tritium is the fuel that we're using. There's not much tritium in the world. We don't want to be wasting this. We don't want this to be trapped in the components facing the plasma. So it's really important that we control this and have adequate measures in place to kind of maintain our tritium inventory. And then, although this is not an exhaustive list, we also have corrosion as well. So between our coolant flowing and the material surrounding our coolant pipes as well, we can also have corrosion. So as you can see, there's a huge suite of problems that leads to developing materials for fusion being a huge challenge. So if we talk specifically about the divertor region, taking into account all these challenges that I've just mentioned, what are the materials that we can potentially use? So here we have our periodic table. If we think just about the heat loads and the melting point, the ones with darker colors obviously have the higher melting point. So this narrows down our selection quite significantly. So you can see here kind of a range of materials that could be suitable if we only think about melting point. When we think about thermal conductivity, this gets even smaller. Availability and cost, which is a very important thing to consider, which I didn't mention in the last slide, but that's always something we have to consider as engineers and material scientists. The options get even less. And then if we think about activation, it's even less. If we include our neutron and radiation damage, it's even less. And finally, we're only left with tungsten. However, this hasn't always been the case. I'm sure you're all aware the majority of tokamaks in the past, and some of them still, use CFCs. And this is a really nice kind of diagram that compares the performance of CFCs in tungsten from the literature. The reference is at the bottom of the slide. But in both cases, we can see as the heat flux factor increases above the damage threshold of around 10, we get cracking, we get melting. So there's real issues with both our CFCs and our tungsten. In order to deal with this, a lot of people have been trying to investigate different composites and looking at different types of material engineering. So I'm going to go through a few from the literature. This is, again, by no means exhaustive, but these are some really interesting ones that have been developed over the past few years. So we've had this tungsten coating on top of graphite, tungsten on CFC. We've had these high entropy alloys. This is a tungsten, tantalum, vanadium, chromium film that's been developed. We have had tungsten fibers inside tungsten, silicon carbon fiber composites, and also microdiamonds in tungsten. So a huge range of things have been developed in order to try and deal with these difficult issues that we've already discussed. So that brings us on to diamond. Now, in the scope of this talk, we're talking about CVD diamonds, so not the diamond that you get out of the ground. CVD diamond was first successfully produced in the US in the late 1960s, as well as in Russia and Japan in the 1980s. So here on the left, we can see the carbon phase diagram, and we can see the conditions under which diamond can form up here at the top. And you also have metastable diamond formation on the left here as well. This kind of shows the formation conditions that we need in order to produce CVD diamond. So you can see at the top, hopefully you can see my mouse out there, these are the kind of conditions where we can produce diamond by CVD methods. Now, for fusion applications, this was actually first reported by Stoneham et al., I believe, in around 2000. And also Ewan Matthews, who's a professor at University of Manchester as well. And they believed that there was a huge scope for using CVD diamond as a coating in fusion environments due to its very favorable properties, which I'll show on the next slide. So diamond has amazing thermal conductivity properties and fantastic thermal shock resistance. Its melting point is pretty decent, and it's actually quite resistant to neutron damage as well, which is very different to the CFCs that we discussed previously. The only kind of limiting factor is that the erosion resistance, while not terrible, it's actually, it performs better than CFCs in many scenarios. It still has some kind of poor erosion resistance compared to tungsten for sure. However, the fact that it does have this neutron damage resistance means that we can requalify carbon as a candidate material through CVD diamond. So this initial kind of suggestion by Stoneman et al. That it would be worth looking at CVD diamond sparked a really comprehensive range of studies in the early 2000s. These are some of the papers here, and I do recommend you read them if you're interested in this area of research. And also Steve Lisko, who's here today, was one of the drivers behind this also. So in this work in the 2000s, my colleagues, they produced CVD diamond here on a molybdenum substrate. So this is the chamber where they produced the CVD diamond, and at the bottom here you have an SEM image of that. And this is kind of a photograph of the CVD diamond on like a molybdenum billet that was placed inside mast. So you can see it here on the left. This was placed inside mast. After it was placed in there, the film remained intact, but the molybdenum did melt, and you can see that there's molybdenum all over the surface here as well. In addition to only looking at kind of a thin film of CVD diamond, they also looked at boron doped diamond as well, which they placed inside mast, and you can see that they put a tile of the boron doped diamond here in the bottom, and this performed really well. There wasn't any arcing, and it had a really great kind of performance within mast. They also placed this boron doped diamond in other devices, so they exposed it to linear plasma devices, so like Pilot PSI and Pisces B as well. And they also exposed it in Judith as well to see the performance, both in terms of erosion performance and, most importantly, the thermal shock resistance. So this is a paper by de Temmerman et al. Where they exposed the boron doped diamond in the Judith electron gun facility, and the thermal shock resistance was far superior to tungsten, and they had no surface damage after 100 cycles at 2.5 gigawatts per meter squared. Now, I've said this number, but just to put that in perspective, if we go back to this diagram, which we had at the beginning of the talk about the damage threshold of pure tungsten and CFCs, the performance of the CVD diamond, all the way over here without damage. And I love this quote at the bottom here saying, "I've never seen anything like it." So a very strong performer, unrivaled, unparalleled. You know, we're talking almost Elm type loadings here in Judith. So absolute fantastic performance. Now let's go back to the kind of design constraints we have for PFC components and what we need to consider in a reactor. So as I mentioned before, we need to think about the neutron resistance. We need to think about the response to tritium. Can we engineer it? Can we actually make this, manufacture it, you know, develop a supply chain? How long will it last for? And can it be done over a larger scale? And specific to PFCs, things like your electrothermomechanical stress, leading edges, the compatibility with the plasma, the fuel cycle, and also importantly, the surface effect performance and the bulk kind of properties of your materials as well are things that we need to consider. So the design question that I'm asking, and I'd like to ask all of you as well, can a composite material be developed that combines the best properties of the qualifying elements? So in terms of what I've been talking about, can we combine the excellent properties of the diamond with the really good kind of plasma resistance properties of the tungsten? So the tungsten really doesn't erode so much compared to diamond. So can we have a CVD diamond layer, and then on top of that deposit tungsten on top of this, whether that's via sputtering or laser processing. So if you just imagine that would be your component, and then you would have a plasma kind of coming down onto that. I mean, I think it's pretty interesting, and this is kind of a project that we've got starting at Manchester, hopefully in September, a PhD project on this very problem. We're going to be trying to produce this with colleagues. If this is successful, could there be a second stage where we kind of distribute the tungsten in between layers of CVD diamonds? So we maintain the bulk properties of the CVD diamond, but have this kind of tungsten as a protective layer on top of it, so you're not getting huge amounts of erosion as you would if it was purely CVD diamond. But when you do remove the tungsten layer, it's very, very thin, of the order of microns, so it shouldn't impact the plasma too much. And it kind of becomes a quasi self-healing material. So if you remove the tungsten layer, there's another layer of CVD diamond underneath, but you're still keeping those bulk diamond properties, which in terms of thermal shock resistance is just unrivaled. So that's what the project is that we're hoping to start soon. And yeah, if anyone is also interested in that or would be interested in collaborating, please do get in touch. So I know I've whizzed through all of that, but in summary of the talk, plasma facing components have many issues that they have to deal with, and the CVD diamond has been shown to have excellent properties. One thing which I've not mentioned actually in this third bullet point, which I should have said before, is that diamond is very expensive. I feel this is a question that always comes up. How can we afford to have, you know, diamond in our tokamak? But there's actually been huge advances in CVD diamond production over the last few years, and it's really ramping up, and the prices could potentially come down quite significantly, which would, you know, make it quite feasible for a fusion reactor. Having the tungsten coating on top would hopefully kind of minimize the, you know, issues of erosion, and also avoid cascade failure of diamond as well. Thank you very much for your attention. If anyone has any questions, please do ask.
Okay, thank you, Aneeqa. Very interesting. Yeah, people now can subscribe to our channel in the social media and YouTube. And now is open the question and answer. Already we have one question from Andrea.
Yes, hello. Hi, Aneeqa. Thank you for a nice talk.
Thank you.
I have a question which is related to the open question that you asked at the end. So whether it is possible to create such a combined material. And my question is, does the CVD technology works with all the substrates for a diamond, or there must be some match, for example, between the lattice of diamond and the material on which you are depositing it?
So I think it will definitely be a challenge getting the tungsten to adhere well with the CVD diamond. I mean, they have very different properties, so it's not straightforward. The good news is that it has been done before in terms of depositing tungsten on carbon. This is what's been done in JET. They deposit tungsten on the carbon. And there's also potential to have a molybdenum interlayer or other types of interlayers as well, which could also help with the kind of adhesion between different types of materials.
Okay, perfect. Aneeqa, I have a question for you. In this case, it's not only the price, but my question is more related with the fast neutrons. Did you have studied the case, for example, on a demo scenario where the plasma is working long periods with the quantity of fast neutrons? I don't know exactly, but this structure, the diamond structure, I think it was sp3, can be resistant to these fast neutrons.
So I've not done any modeling on this myself, but in terms of neutron resistance, it does have, you know, in the literature, it seems to have quite good neutron resistance. But yeah, I think definitely this is a new project, so it's something we need to consider going forward.
Okay, thank you. Okay, we have another question. Paul Goodwin, yeah, you can talk now. Okay, Paul, go ahead.
Your idea of interlayers, what sort of layer thicknesses are you thinking?
I guess of the order of 4 or 5 microns, order of microns for interlayers.
Right. Okay. So that rules out any other techniques like additive manufacturing and powder hipping or anything else in order to make the interlayers.
Although actually, so additive manufacturing is a really interesting one, and one that I'm really intrigued by, and I want to explore further. So there is a company called Sandvik. I don't know if you've heard of them.
Yeah, very much so, yeah.
Yeah, so they have produced, I believe, additively manufactured diamond very recently, but obviously it's quite hidden by, you know, the proprietary kind of information. So I do think there would be scope for added. I mean, that would be ideal, right? If you could additively manufacture this, but it would just, it's a huge materials challenge, like getting the right properties and the densities and things like that.
Yeah, it's a challenge. So
yeah.
I'd be interested in talking to you sort of offline separately. So my background is powder metallurgy, and particularly for the last 20 years, additive manufacturing.
Oh, fantastic.
And we've been thinking about layering tungsten with various things, possibly on a more of a macro scale than you're looking at. But
okay.
Yeah. So yeah, I'll follow up with you somehow.
Yeah, that would be great. I can put my email address in the chat actually, and it'd be great.
Please do. Please do.
Yeah. Oh, great. Thank you, Paul.
Okay, thank you, Paul. Well, then thank you, Aneeqa, to the nice talk. It was quite interesting, and we are waiting for new results in the future. It's quite interesting. And thank you, everyone, also for attending the talk. And see you in the next talk.
Thank you so much.
Okay, guys. Bye.
Bye.